Hey folks, how's it going? So in this section, we want to study analyzing the graph of a function. In other words, we want to put together everything we've learned in this chapter so far using applications of derivatives, or almost everything we've learned, to come up with a great looking graph of a function by hand. So we want to be able to address where is a function increasing, where is it decreasing, where does it have relative maximums, relative minimums? Does it have absolute maximums, absolute minimums? What about the concavity? Is it concave upward, concave downward? Where are inflection points? So that's all the calculus side. And then we want to use the pre-calculus skills we've learned before this class, like what are the x-intercepts? What are the y-intercepts? Does this graph have symmetry? Does it have vertical asymptotes? Does it have horizontal asymptotes? So we're going to put all that together and try to come up with good-looking graphs of functions, and then we can always go in Desmos and type it in and see if we did it correctly. All right, so I have some guidelines for you. So let's go through all the guidelines first, and then we'll do a few examples. And warning, these examples take a long time. All of these problems take a while. So be prepared to sit down and put some time into this homework. Just to do a single problem, it takes a little while. All right, so guidelines. Well, the first thing we need to do is find x-intercepts of the function. And by the way, these guidelines aren't really in a specific order, but this is a good guideline to follow. So first you want to find x-intercepts of the function. You know how to do this, right? I'll certainly remind you, if you don't, you set the function value f of x equal to 0 and solve. Often you might have to factor to do this. Sometimes the quadratic formula could potentially help you out. Notice over here I said this may be a challenge for some functions, even impossible. That's true. You can't solve every single function equal to 0. That is not always possible. There are plenty of polynomials that you would have to do that numerically. You do the best you can. If you can find the x-intercepts, you find them. If you can't, you might need to approximate them some way or another. Second thing you need to do is find y-intercepts of the function. Now everybody knows how to do that, right? To find a y-intercept, you substitute x equal to 0. Now that is always possible. Now, I'm not saying every function has a y-intercept, but it is always a possible problem to substitute 0 in for x and just simplify. It's just a numerical problem. There is no algebra really involved in finding a y-intercept. Third thing, vertical asymptotes. Now, we learned in a pre-calculus course how to find vertical asymptotes. Simply, you set the denominator equal to 0 after the function has been simplified. So don't do that before the function has been simplified. You have to do it after the function has been simplified. But we also know now from a previous section that if you take the limit as x goes to a particular value and you get plus or minus infinity as the result of your limit, which means the limit doesn't exist, but it tells you that you also have a vertical asymptote. So we'll be finding those. Fourth step, find horizontal asymptotes. Now on the other hand, if you take the limit as x goes to infinity and you get a numerical value, a real numbered answer, and that says you go to plus or minus infinity, then you have a horizontal asymptote. So we learned about vertical asymptotes in the limit chapter. We learned about horizontal asymptotes in the previous section that you did before we talked about analyzing the graph of functions. Okay, now I have another step for you. Step 5, find a slant asymptote. Now this might be something that you have never done before. Notice it says, only for rational functions with the degree of the numerator, right here, only for rational functions with the degree of the numerator 1 higher than the degree of the denominator. It says you need to use long division to divide, and then the slant asymptote is y equals the quotient. So you might want to keep this in your notes close at hand. We will definitely try to do a problem with a slant asymptote. But y equals the quotient. The remainder doesn't have anything to do with the slant asymptote. So for an example, and I'm not going to do a full example right here, but a problem like this, like if you had x squared plus 1 over x, that's what I mean about the degree of the numerator is 1 higher than the degree of the denominator. The numerator is degree 2. The denominator is a degree 1. So how would you find the slant asymptote? You would divide x into x squared plus 1. Remember, I have to do that. You have to put in dummy values for missing exponents. So it would be x squared plus 0x plus 1. Then you ask yourself, what do you multiply x by to make it an x squared? And it would be x, and then you do x times x is x squared, and then you subtract and you pull down the 0x plus 1. X doesn't divide into 0 at all, okay? You could put plus 0 if you wanted to. But basically, there's your quotient right there, and your remainder is 1, okay? So the answer is x plus 1 over x. You could also split this fraction up to figure that out, but I wanted to show you long division. But this would be your slant asymptote. It would be y equals x. Okay, that's the quick version. I wasn't planning on doing a problem right then, but I just threw one out just so you could see it. But we will do that in the middle of doing a problem. At least I think one of my examples has that. If not, I might have to add an example, huh? Now, step 6. Find the derivative and make a chart including the intervals separated by critical numbers. You know how to do this. When you make that table and you find increasing and decreasing intervals by checking test points to plug in your chart. Okay, so we'll do that. Step 7, find the second derivative and make a chart including intervals separated using critical numbers of the second derivative. Concave upward and concave downward comes from that, and also inflection points. Now, to me, these are two different charts or tables. You could make one big table including all this, but I have found that the information is a lot easier to follow if you do a separate table for the first derivative and the second derivative. That really is up to you, but that's my way of doing it. All right, not finished either. Other thing that might be helpful is symmetry, the domain of the function we need to talk about, and solve f of x equals your horizontal asymptote. So say you have a horizontal asymptote of 5. If you set your function value equal to 5, you could find out if your graph intersects the horizontal asymptote. So these are extra things that may help you graph. You don't necessarily have to find them for every, I don't know, domain's pretty important. You might want to find that for every function that you graph. But all of this, not necessarily, but we need to go through these steps every time just keep ourselves organized. So let's do a problem. So our very first problem, we're supposed to sketch the graph of f of x equals x squared plus 1 divided by x squared minus 2. So I have a list of things. You'll notice all of these things are listed in the guidelines. I may or may not have enough space right here to get all this done, but I'm going to try to stay neat and organized and talk to you about how you would find these things. So you know to find x-intercepts, you substitute f of x equals 0. So what we're supposed to do, I'm going to put in red. Okay, now what we are doing, I'm going to do in blue. So I'm setting this function equal to 0. So I have 0 equals x squared plus 1 divided by x squared minus 2. Now we know how to solve an equation like that. At least we should, right? The rule is to multiply both sides by the denominator. Why? Because I can't solve for a variable if it's living in the denominator, right? I have to have that out. So those cancel. Now what I'm left with is a 0, because x squared minus 2 times 0 on the left is still 0. On the right I have x squared plus 1. Now, goal is to solve for x, right? This is a quadratic equation, so you could use the quadratic formula. It does not factor, but we can use the square root property. We can subtract the 1 to the other side. Then you take the square root of both sides. Now, you know when you add the square root as a tool, you must put a plus or minus in front of one of the sides. But what do you notice from this? You know the square root of negative 1 is an imaginary number, so you get solutions of plus or minus I. But here's the deal. That's not real. In calculus, we are only dealing with real valued answers. We're graphing, right? So only real value numbers matter. So what does that mean? Well, it means we have no x-intercepts for this problem. None at all. Now, does that not seem helpful? No, it's very helpful. We know we don't cross the x-axis at all when we graph this function. Okay, now how do you find y-intercepts? You know how to do that, right? You substitute x is equal to 0. So the how-to is in red. For this particular problem, I'm just going to plug in 0. Now, I can't call this f of x. I'm just going to say y equals instead, because they are the same, right? So 0 squared plus 1 divided by 0 squared minus 2. 1 divided, this is 1 in the numerator, negative 2 in the denominator, which gives me negative 1/2. So in point form, x is 0, y is negative 1/2. So we found the y-intercept. Vertical asymptotes. Now, vertical asymptotes when you happen when you simplify your function completely, okay, and it's where the denominator is equal to 0, okay. Now, by definition, in calculus, what that means is if you take the limit as x goes to a particular value, you get plus or minus infinity. But the fact is, to find that particular value, you have to do it the way you did in a pre-calculus. You have to know what value to take the limit to. In other words, set the denominator equal to 0. So simplify first. Always simplify. And then you set the denominator equal to 0 and solve. Okay? So, you know what? This guy doesn't simplify. X squared plus 1 over x squared minus 2, that does not factor. And if I just set that denominator equal to 0, I add my 2 over, I use the square root property, and I get plus or minus the square root of 2. Now, we could go through the extra work, which, by the way, I'm going to do this in green. These are, without a doubt, my vertical asymptotes. That is them, okay? But you know what? It would help to know if when we take the limit as x goes to the square root of 2, from the left, what do we get? And as we take the limit as x goes to the square root of 2 from the right of our function, what do we get? I'm just going to put f of x in here, okay? And on the other side, if we take the limit as x goes to negative square root of 2 from the left of our function, what do we get? And as we take the limit as x goes to negative square root of 2 from the right of our function, what do we get? Now, why would you need to know something like that? We know we're going to get either plus or minus infinity. That's what makes it a vertical asymptote. But it would help us graph it. That's really good information. Now, let's think about this. If I plug in a number, look, just a little less, because it says from the left, right? Just a little less than the square root of 2. Now, I'm going way back to the top of my page and plug it into that function. Now, you're talking about a number a little less than the square root of 2. When I square it, it's going to be a little less than 2. When I add 1, it's going to give me a positive number, right? Well, when I plug in square root of 2 in the denominator, okay, a little less than the square root of 2 because it's on the left side. That's going to be a little number a little less than 2. Minus 2 is going to give me a negative number. And that's going to go to negative infinity. Okay, now you have to know it goes to plus or minus infinity first before you pull that stunt. You realize that, right? You can't just do positive or negative and every time it's plus or minus infinity, because if you could plug in square root of 2 and get an answer, then that would be the value. But if you plug in square root of 2, remember you get 0 in the denominator. Okay. All right, now if I plug in square root of 2 from the right, if I plug that into the numerator, I get a positive no matter what. If I put square root of 2 a little bigger than square root of 2 into the denominator, that's going to give me a number bigger than 2 minus 2 is positive, so that's going to go to plus infinity. All right, now let's look at as we go to negative square root of 2, which is probably what I should have done first, but I didn't. Now, we're talking about from the left, so you're talking about a number a little less than negative square root of 2. Okay, like negative square root of 2, really close, but a little less than that. When I square that, that's going to be positive, and I add 1 to it, it's still positive. But in the denominator, when I square it, it's going to be a number bigger than 2. Minus 2 gives me positive. So it goes to plus infinity on that side. Now when we plug in a number to the right of negative square root of 2, on the top we still have a positive. Again, because you're squaring it and then you're adding 1. It's got to be a positive number. In the bottom though, a number to the right of negative square root of 2, and then I square it, is going to be a number a little smaller than 2, and then I subtract 2 is going to give me negative, so that goes to negative infinity on that side. Okay, so this is the behavior at the vertical asymptotes. It's good information to have. All right, how about horizontal asymptotes? Now that's just a straight up calculus move. You can remember how you did it. back in a pre-cal class, you compare the degree of the numerator to the degree of the denominator. If you remember that, whenever the degrees match, it's y is equal to leading coefficient over leading coefficient, so you get y equals 1. So I know that's my answer. But now what you're really supposed to do in a calculus class, you're supposed to take the limit as x goes to infinity of your function, x squared plus 1 over x squared minus 2. This is what you did in the last section, and you're supposed to take the limit as x goes to negative infinity also of x squared plus 1 over x squared minus 2. Now how do you do that? Well, what you're supposed to do, remember, is multiply by 1 over the highest power in the denominator. So 1 over x squared in both the numerator and the denominator. And again, that's why I chose that. Now in the numerator, that gives me, here we go, x squared times 1 over x squared is 1, plus 1 over x squared divided by 1 minus 2 over x squared. Remember, I'm still taking the limit as x goes to infinity. That goes to 0, that goes to 0, and that gives me 1. Okay, we already knew that was going to happen by the pre-cal method. But now, this is the same story over here, y'all. You still get, for the same exact reason, you multiply by 1 over, doesn't matter that you're going to negative infinity, 1 over x squared on both the numerator and denominator. Again, when I distribute that 1 over x squared inside, that's x squared times 1 over x squared, which is 1, plus 1 over x squared. That's x squared times 1 over x squared, which is 1, minus 2 over x squared. You're taking the limit as x goes to negative infinity. So that goes to 0, that goes to 0, and my answer is 1. Okay? So now we have a horizontal asymptote. Slant asymptote, remember, they only happen when the degree of the numerator is 1 more than the degree of the denominator. So the degree of the numerator is 1 higher. And you know what? That is not happening here, right? The degrees are the same. Degree of the numerator is 2, degree of the denominator is 2. So it has no slant asymptote. So let's move on to the next thing we're supposed to do. We're supposed to do our first derivative chart, right? Well, to do a first derivative chart, remember it finds increasing and decreasing, relative maximums, relative minimums, but the very first thing I have to do is take the derivative. So let's do that. Now notice, I probably need to split this into 2 different pages, folks. I'm going to do that now before we do any more. Hold on just a second. Okay, that's better. I don't know what in the world I was thinking, trying to get both the first and the second derivative chart on the same page. So here we go, the first derivative. So I have f prime of x. Now this is a quotient rule, right? So I got low d high minus high d low over low squared. So low is x squared minus 2. D high, or the derivative of the numerator, is 2x. Minus high, x squared plus 1. The low derivative of the denominator is also 2x over low squared, or x squared minus 2 squared. I'm going to simplify that as much as I can. Then I'm going to find critical numbers. Now what you should do when you're simplifying is factor any common factors if you can. And notice, look, there's a 2x in both of these terms, so I'm going to pull that out front. 2x comes out. And that's going to leave me with x squared minus 2 minus, now this minus is going to distribute. I'm going to go ahead and do that to save space. X squared minus 1. You're used to that kind of stuff by now because you've been taking first and second derivatives for a while now. Okay? Now I'm going to add like terms. This x squared and this minus x squared cancel, which is kind of fancy. And this minus 2 minus 1 is minus 3. So now I have 2x times negative 3 over x squared minus 2 squared. Continue to simplify. That's going to give me negative 6x over x squared minus 2 squared. Now remember what you're supposed to do to find critical numbers. So remind me, what do? Well, you take the derivative and you set it equal to 0. And you also have to find out where the derivative is undefined. Okay, now if I take this derivative, this guy right here, and I set him equal to 0, You remember, a fraction equal to 0 is really the same as the numerator equal to 0. I would multiply both sides by x squared minus 2 all squared. Well, yeah, that's just going to give me 0 equals negative 6x. Again, something you've seen a bunch of times by now, I feel certain. So I divide both sides by negative 6. That gives me x equals 0. That guy is definitely a critical number. Now, where's it undefined? If I set the denominator equal to 0, remember, undefined happens when your denominator of your derivative is equal to 0. That's what you're really doing there. Well, that would be x squared minus 2 equals 0. Well, it's squared, right? Which, take the square root of both sides, that's x squared, minus 2 equals 0, gives me x equals plus or minus the square root of 2. Well, remember, those were vertical asymptotes. Our function is not even defined there, so those are not critical numbers. But now, don't just throw them aside, because you still have to include them on your chart, okay? So I'm going to come over here and do my chart now. My chart. I have to think about the domain of my original function, which is negative infinity to infinity, but you got to take out that plus or minus square root of 2 because that's what makes the denominator 0. So here's what we're going to do. For our chart, we're going to go from negative infinity to negative square root of 2, okay? Then we're going to go from negative square root of 2 to 0, because 0 is a critical number, right? Then we're going to go from 0 to positive square root of 2, and then finally from positive square root of 2 to infinity. So there's my table, and I thought I was going to fit this on half a page. That'd do good to get all this on this page. There we go. All right. Now remember, next, what am I supposed to do? I'm supposed to test a point. So we're going to test a point here. In other words, we're going to find a point to test. Okay. And then, where am I going to plug in that test point? I'm going to plug it into the first derivative. Okay. And then, my last line is my conclusion. Now, you know when I'm dealing with the first derivative, your conclusion is whether you are increasing or decreasing. So that's what should be in this bottom line down here. Am I increasing? Am I decreasing? Now, what values would you like to use? Okay, well, I need something between negative infinity and negative square root of 2. Now, you know negative square root of 2 is about negative 1.4, right? It goes on forever. So let's try negative 2. Now, something between negative square root of 2 or negative 1.4, 1, and 0 would be negative 1. A value between 0 and square root of 2 would be positive 1. And then finally, a value between square root of 2 and infinity. Well, 100 would work, but 2 is a lot smaller, so let's go with 2. And remember what I'm doing now. Don't forget, I'm plugging those into the derivative, not the original function, the derivative, because that tells me whether my function is increasing or decreasing. So here I have negative 6 times negative 2 over something squared. Let's do that fast. Y'all know something squared is always positive. Am I right? Negative 6 times negative 2 is also positive. A positive divided by positive overall is a positive. What does that mean? Well, that means we're increasing on the interval negative infinity to negative square root of 2. Okay? Next interval, let's plug in negative 1 into the first derivative. So I have negative 6 times negative 1 divided by something squared. Okay, now something squared in the denominator is always positive. Negative 6 times negative 1 is also positive. A positive divided by positive overall is a positive. So I'm also increasing on the interval negative square root of 2 to 0. Careful, these do not always alternate, especially when you have a rational function. Okay, you have to check every one of these intervals. Then I plug in 1. Negative 6 times 1 over something squared. The negative 6 times 1 is a negative number. Something squared is a positive number. A negative divided by positive overall is negative, so we're decreasing. Finally, I plug in 2. Negative 6 times 2 is definitely a negative number over something squared, which is a positive number, and a negative divided by positive, just like it was a second ago, is negative, which means I'm decreasing. Now remember, the rule is when you change from increasing to decreasing or decreasing to increasing, you might have a relative max or a relative min. So right here, we didn't change at all. Not only that, negative square root of 2 was undefined in the first place. Okay, so even if it did go from increasing to decreasing, this would not be a relative max or a relative min. It's a vertical asymptote, right? But right here, we're going from increasing to decreasing. Now, the first derivative test tells us that that is a relative max because it goes up and then goes back down. So we have a relative max at 0. Now, 0 was a real critical number, so we do have a relative max at 0. And then here, there is no change. So what else did we find out other than the intervals is that we have a relative maximum at the point. Okay, now it's at 0, your x value is at 0. Now how do I find out what the y value is? You go and plug 0 right back up in your original function, which would be 0 squared plus 1 divided by 0 squared minus 2, which is actually negative 1/2. That ought to be familiar. That was also your y-intercept. Do you remember that? You may not, but it was, okay, way back a few minutes ago. Now we need to do all this for the second derivative to find out about concavity, and then we can finally put all this information together and graph our function. All right, folks, so now we're working on the second derivative and the chart associated with the second derivative. You can't take the second derivative unless you know what the first derivative is. And I recopied it, but I am going to go back a page just to be certain. And there it is at the bottom of the page, negative 6x over x squared minus 2 all squared. So I did write it correctly. Now let's see if we can't take the derivative. I've got to use the quotient rule again, right? So I have f double prime of x. I'm going to try to keep this organized. I have low d high. So low is x squared minus 2 all squared. The derivative of the numerator, or d high, is negative 6. Minus high, which is negative 6x. And then d low, I got to use the chain rule, right? I got to pull the 2 in front. Rewrite the inside exactly the way it is. Reduce that exponent by 1 times the derivative of the inside, which is 2x, all over low squared. So the denominator squared, it's already squared, so I square it again, and that gives me to the 4th power. Now my goal now is to simplify this as much as I possibly can. I do have some greatest common factor I see of 6 or negative 6, depending on how you want to handle that. Also have factors of x squared minus 2 I could pull out. Let's do that. So I'm going to pull out that common 6. Okay. I don't think I'll worry about the negative right now. You could pull out the negative. I'm just going to make it a... no, let's pull out a negative 6. That'll be easier to look at. So this negative 6 comes out. Also, I wrote too quickly, also an x squared minus 2. They both have an x squared minus 2 in common. There it is. It's out. Alright, so negative 6 and an x squared minus 2, which still leaves me with an x squared minus 2 inside. Okay, now this negative 6 is out. I'm going to highlight it. So we pulled that out. We pulled out one of those. We pulled that out, and we pulled out one of those. Now, what does that leave me with? Okay, so there's still a minus in between. Okay, I still have a 2 and an x and a 2x. So that's going to give me 4x squared is the way I see that. Over x squared minus 2 to the 4th. Make sure you feel good about that. Okay, so I pulled out again here, because I only pulled out one x squared minus 2, it left me with an x squared minus 2. The minus 6 is out. Here I pulled out that minus 6, I pulled out that x squared minus 2, so it still leaves a minus in the middle, and it still leaves this 2x here times this 2x, yes, is 4x squared. I think that's it. Now I keep simplifying. F double prime of x is equal to negative 6. Now, look, I can cancel this x squared minus 2 with one of those guys, and that makes it to the 3rd now. And in the brackets, I have x squared minus 4x squared, which is minus 3x squared, and then minus 2 over x squared minus 2 to the 3rd. Now, if you wanted to, you could distribute that minus 6 back inside. It really doesn't matter. Doesn't matter that much at all. That would be 18x squared plus 12 over x squared minus 2 to the 3rd. Either way, or you can leave it factored out. What am I doing with it? I'm setting it equal to 0, and I'm finding out where it's undefined. Now, fact is, look, It's undefined where that same old denominator, except raised to a different power, is equal to 0. So what I'm really focused on is where's the thing equal to 0. So 18x squared plus 12 over x squared minus 2 to the third is equal to 0. Now you know what we do now. We multiply both sides. I don't want to do that in red. Let's do it in black. By the denominator, because you can't solve for an equation when there's a variable in the denominator. Or you try not to anyway. Those cancel. So basically I have 0 equals the numerator. And I solve that equation by subtracting 12 and dividing by 18. Okay, so that's going to give me negative 12 over 18 is equal to x squared. Well, look at there. Can I take the square root of that? Well, you sure try, right? But I get an imaginary number. I get plus or minus the square root of that, which is none. We don't get any critical numbers from that. Does that mean we don't do a chart? No, not at all. We still have a chart we have to do. We just don't have any critical numbers for the second derivative. But the fact is, our chart splits up with those vertical asymptotes. Remember where the function is undefined? So we're going to go from negative infinity, okay, to negative square root of 2. Then we're going to go from negative square root of 2 to positive square root of 2. Remember, we don't have to go to 0 because 0 is not a critical number for the second derivative. Then we're going to go to square root of 2 to infinity. So that is our chart. Again, like I thought I was going to do this all on one page. Okay? Now, remember on our chart, we have to pick some test points that go in our interval. Okay? We have to plug that into the second derivative to figure out if we're concave up or concave down. And then we have our conclusion, which again is the concave up, concave down stuff. So a number between negative infinity and negative square root of 2 would be, say, negative 2. A number between negative square root of 2 and square root of 2 would be 0. And then a number between square root of 2 and infinity is positive 2. Where am I plugging those into? Into the second derivative. So, y'all, I'm going to highlight it down here. I'm going to use that guy right there. That's where I'm going to plug it into. Okay? So let's do it. Now, in the numerator, if I take negative 2, and I plug it in right there, and I square that, that's going to be 4. 18 times 4 is positive, plus 12 is positive. So that numerator is positive. I think everybody can see that. We've got to think a little bit harder in the denominator. Since it's raised to an odd power, I can't just say that whole answer is positive without thinking about it. But if I take negative 2 and square it, it's 4. 4 minus 2 is 2 to the third is 8. So it's positive in the denominator, which overall gives us a plus. What does that mean? That means we are concave upward. All right, on the interval negative infinity to negative square root of 2. Now if I plug in 0, okay, 0 in the numerator is going to give me a positive 12, so it's positive. 0 in the denominator is going to give me a negative 8 because that's 0 squared, which is 0, minus 2 is negative 2, negative 2 to the third is negative 8. Positive divided by negative overall is a negative, so I am concave downward on that particular interval. Finally, when I plug in positive 2, okay, positive 2 into the numerator is going to give me a positive because I've got 18 times 4 plus 12, definitely a positive number. Into the denominator, I've got 4 minus 2 is positive to the third is still positive. So we're back to positive, so I'm concave upward. Now normally I would have, you know where it changes concavity, like upward to downward, this guy right here where it changes would be called an inflection point. But this doesn't have any inflection points. You know why? Because that happens at vertical asymptotes. This function is not even defined at negative square root of 2 and positive square root of 2. So we can say there are no inflection points. Now the good news is this. Even if you thought, hey, negative square root of 2 is an inflection point, you'd pick that guy up and plug it into the original function. You would see you get a 0 in the denominator. Then you would go, oh yeah, negative square root of 2 is not even in the domain. Okay, so you have a way to check yourself on that. Now what I want to do is summarize all of this information because it's 3 full pages of packed material on one page and see if we can pull a graph together from all that. Okay, folks, here you go, a summary of everything. So if you'll remember, we had no x-intercepts. We had a y-intercept, just one of 0, -1/2. Matter of fact, every function only has one y-intercept or less, because it wouldn't be a function otherwise. Vertical asymptotes, we had two, one at -√2, one at +√2. As a matter of fact, it probably would not hurt to go down your graph. I'm going to do this in maybe green, okay, and do your dashed line. So remember, √2 is about 1.4, so I'm going to do the best I can at about 1.4 and draw my vertical dashed line to remind myself my graph cannot cross that. That's +√2 and also at -√2. Your graph could look much better than this because my scale maybe not be, could have been smaller to pull this off. We'll see, okay, how it looks. Now, I'm going to keep going with this. I'm graphing in red. 0, -1/2. Let's plot that point. So 0, -1/2, right there. That's my y-intercept. Horizontal asymptote. So in green dashed line, I'm going to plot the horizontal line of y = 1. Now, here's the thing. Are you allowed to cross a horizontal asymptote? In fact, yes, you are allowed to cross a horizontal asymptote. Now, what we could do to find out if we cross that horizontal line is we could set the horizontal asymptote 1 equal to our original function, x² + 1 over x² - 2, and solve that equation. Now, I'm going to work down in green because it's going to look confusing. I'm going to multiply both sides by x² - 2. Well, look what happens. If I subtract x² to get it all on the same side to get the equation -2 = 1, you can't solve that. So it does not cross, or intersect is a better way to say it, the horizontal asymptote. So we are never going to cross the line on this particular graph. So that's one of those extra little things that we talked about when we did the guidelines at the end that you could find out. There is no slant asymptote. Notice we're increasing from -∞ to -√2. So I know my graph is increasing from out here to out here. Okay? Now, the only way to draw that, think about it. If it's got a horizontal asymptote and approaches, it cannot be down here. The graph has to be up here. Now, what I didn't include was the behavior of the graph. Y'all, if we go back to that first page where I was doing all that work, and you'll see it in your notes, what is the behavior of the graph as we go to -√2 from the left? So let's find that. This is in green. The limit is x goes to -√2 from the left. Right over here goes to +∞. And if you'll notice, that's exactly what we did right there. We went to +∞. Okay? Now, we're also increasing from -√2 to 0. Okay, so that's between here and here. So my graph is going up like that. We're decreasing from 0 to the square root of 2. So I'm going down. Decreasing graph, right? And I'm also decreasing from square root of 2 all the way out to infinity. So it's decreasing. Now we could go back and check the behavior of our graph, right? As x goes to -√2 from the right, it was going down to -∞. I bet, let's check it. As x goes to -√2 from the right, look, it's going to -∞. As x goes to +√2 from the left, look, it's going down to -∞. Let's check that. So as x goes to +√2 from the left, look, it's going to -∞, just like we thought. And then finally, as x goes to the square root of 2 from the right, it says it's going to +∞. So let's look. As we go to square root of 2 from the right side, it's going up to +∞. And there's our graph. Now, we could type this into Desmos. I'm not, just to save a few minutes, but I promise you, I think you should pause it and stop right now and type this graph into Desmos so you could see what it looks like. Now, notice I did a rough sketch. I did not plot any points. You know, this could, you know, where it crosses through could be in a different place, but I've got the behavior of the graph correct. Here's another thing. We had a relative maximum is 0, -1/2. Notice that matches, but there are no relative minimums. Okay, we are concave upward. Notice I didn't even address that. It just matches the graph. We're concave upward from negative infinity to negative square root of 2, and also from square root of 2 to infinity on the right. But in the middle, we're concave downward, which exactly matches the graph. And there are no inflection points because it did not change concavity at an actual point. We had a vertical asymptote that separated the changes in concavity. I hope this helps. I hope you'll come back for the next example that I do, because they take a long time. So I'll probably do 2 more examples for you. All right, have a great day.